Okay, now let's take a couple of examples. This first sequence is easy to deal with. How can we argue that it converges? Well, we already know, because it's such a simple sequence, we know what it converges to, and we can argue it in several ways. We know, for example, in arithmetic of sequences, we know that the sequence 2 converges to 2, and the sequence 1 over n converges to 0. So we know that this is going to converge to 2. But if we didn't know that, we could say that, let's see, it's bounded above by 3. Does that help me though? This is actually a decreasing sequence, isn't it? So I want to say bounded below by what? 2. I could say it's bounded below by 1, yes, but 2 happens to be the special number. That's the greatest lower bound, but I'm not even interested in that. The sequence is bounded below by 2, and it's decreasing. I'll say this one is a strictly decreasing sequence. It goes 3, starts with 3, then 2.5, and so on. That's all the information we need to know that it's convergent. That doesn't tell us what it converges to, but the previous theorem, we just wanted to know that if it's bounded and decreasing, it is convergent. And actually, we know it converges to the greatest lower bound of this when you look at this as a set, and the greatest lower bound would be 2. The next example, coming from the text, it's a recursive definition. I thought this would be worth mentioning. I'm not going to go through all of the algebra required. The first element of the sequence is radical 2. The rest of them are defined like this. We needed to define S1 in order to get S2 because Sn depends upon Sn minus 1. So let's write out maybe 1 or 2 more. The second sequence is going to be the square root of 2 plus the square root of S1. S1 is the square root of 2. Let's see. That is not quite right, is it? Yeah, it's not. I think let's see, 2 plus the square root of the previous one. But there weren't 2 square roots. Anybody have the text open by chance? On 1.6, something doesn't quite seem right.
S2 is square root of...
And what's S? Is S1 radical 2?
Yes.
And S2 is what?
Square root of 2 plus the 4th root.
Oh, it is the 4th root. Okay. Then it is correct. I didn't remember it being a 4th root. Okay, that makes sense because it's a square, it's radical 2. So it's the 4th root. And so on. This is going to get rather ugly very quickly. In the text, they do a good job of algebraically going through all of the proofs required. But let's just look at it in terms of this. Is it bounded above or below? And is it increasing or decreasing? That part should be the easiest part. You should notice that each term we're adding more underneath the radical. So it's an increasing sequence. I'm just going to say easy to see. That Sn is increasing. The rest of it, the tougher part of it, was finding the best upper bound, the least upper bound. I'm just going to write down that it's bounded. Therefore, Sn converges. And I believe in the text they showed that the least upper bound was actually equal to 2. Sn converges to 2. By finding the least upper bound, that tells you that it converges to 2. So I'll just write down that the supremum of the Sn's is 2, and that implies that Sn converges to 2. So this one wouldn't have been so bad if we could just find any upper bound. We would have known that it's convergent. In the text, they go through all the algebra required to show that the least upper bound is 2. And since it's a monotone increasing sequence with least upper bound 2, it means it converges to 2. Sn converges to 2.